Hi, it's Romeo Bruni, and it's time to build a spiral galaxy. The James Webb Space Telescope has shown lately that there's many galaxies that aren't quite what they predicted, especially when they search far back into time. They're finding too many galaxies that are already disk-shaped, and especially very far back in time, more than 13 billion years ago, they're finding galaxies too large and too luminous. I think these findings are easily explained under the standard lambda cold dark matter Big Bang model, especially in terms of spiral galaxy formation. Spiral galaxies are the key galaxy because they are the galaxies that came out of the Big Bang. The vast majority of spiral galaxies in the universe today are indeed spiral galaxies. So if we examine spiral galaxies, we can get big clues into the nature of the Big Bang. Now, spiral galaxies are an incredible, beautiful, scenic thing. Complete, beautiful symmetry. And you wonder, how can something like that pop out of a chaotic Big Bang? And that's what we're going to talk about. What happened with the Big Bang is that it created only two things: hydrogen and dark matter. In the first 4 minutes of the universe's life, it was so hot that the hydrogen was able to fuse and produce helium. So within 4 minutes, you had also helium in the mix, approximately 75% hydrogen, 25% helium. So what was generated out of the Big Bang were these large clouds that contained basically hydrogen, helium, and dark matter. This is evident, actually, when the first light that we can see from the universe is at the cosmic microwave background stage. And at that point, we've actually taken pictures of the universe at that stage. And this is a picture, and we're showing the three different qualities. In 1992, very poor quality. The WMAP in 2003, much greater clarity. And Planck in 2013 showed even greater clarity. And what you're seeing there is an actual picture of the baby universe when it was 380,000 years old. And you can see there's a clumpiness there. These little clumps, represented by differences in temperature, is where matter conglomerated into clumps. These clumps are the clumps that later go on to form galaxies. You can imagine these clumps or these clouds to be like bubbles. And every bubble contains only two things or three things. So let's look at a typical bubble. The bubbles, of course, as you would expect from anything chaotic, would emerge in a Gaussian distribution, which means a bell curve distribution, which means that they're going to be different sizes and they're going to have different compositions. It's a chaotic event. There's no master cook proportioning exact quantities into the clump. So if we can consider a typical cloud is therefore going to contain only three things. It's going to contain hydrogen, it's going to contain helium, and it's going to contain dark matter. The important thing here is that the proportions are always going to be approximately the same. You're going to have 85% of the matter is actually, or the mass or matter is dark matter. 15% is hydrogen and helium. Again, 3/4 of that hydrogen, 1/4 of that helium. So the key thing is that even though the Big Bang was a chaotic event, what popped out of the Big Bang were these large clouds. The only thing that was not chaotic, the only thing that provided the nucleus for any order in the universe, in these galaxy clumps, is that these three things were all given a coherent spin. They were essentially clouds, all spinning around coherently. The hydrogen, the helium, and the dark matter, all spinning coherently. Coherence is the key. In a system like this, because dark matter does not experience friction, it doesn't bump into itself, it's hard for it to accrete. So the dark matter is continuously spinning. And what that does is it accretes the heavier elements, which are the hydrogen and helium, accreting them down to form a disk shape. So in the center of this huge sphere of dark matter continuously spinning, it gradually over time starts to accrete a disk galaxy. These galaxies are accreting down. So it's the hydrogen and helium that accretes down because of the dark matter. The dark matter is the puppet master, which controls the accretion and causes the accretion. Now at the center, and that is why in the early universe, very early, we're starting to see evidence of dark matter because there's, of disk galaxies, because there's so much dark matter there that it's rapidly accreting the hydrogen and the helium. Also, going into galactic structure a little bit closer, at the center of every spiral galaxy, there's a supermassive black hole. It's large. Sagittarius A star, the supermassive black hole at the center of the Milky Way, is approximately 4.2 million solar masses. So it's incredibly huge, but they are not huge enough to accrete the whole galaxy. They only control things in their own local little vicinity, which is very important, of course, because around every supermassive black hole, you're going to get an accretion disk. Accretion disks, just like the accretion disk, which is the whole galaxy from the dark matter. In this case, the accretion disk is going to be your typical type of accretion disk where you have a very central dense object, and matter starts to, as it swirls in, accretes down into a disk and starts to feed matter into the black hole. Every spiral galaxy, except maybe one, and that's still controversial, has a supermassive black hole at the center, so they're part and parcel of spiral galaxies. To look further at what happens there at the center, if you have a supermassive black hole at the center, and then you have an accretion disk that forms, funneling matter into the black hole. As the matter funnels in, it's starting to get hotter and hotter. So at the edges, it's releasing like infrared light because it's not so hot, so it's releasing low energy waves. As it gets hotter and hotter, it's giving off higher and higher energy rays, so that near the center, just before it spirals into your black hole, it's giving off X-rays. X-ray light waves, super high energy light waves. These X-ray light waves beam into the universe and we can see them, and that's why these galactic centers can be very active and we can see X-ray emissions from them. Also, because of the black hole has got a spin at the center, and this local accretion disk helps to create an incredible magnetic field out the ends of the polar axes of these massive spiral galaxies. You start to get the jets. The jets are due to the black hole spinning and creating an incredible magnetic field. So as it turns out, approximately half the matter that gets close to the black hole gets absorbed by the black hole. The other half of the matter gets propulsed out in these incredible jets that are essentially plasma, like electrons and protons moving at a very rapid speed, relativistic speeds, near the speed of light. And when charged particles are accelerated at near the speed of light, especially when they're spinning, they're spiraling like that. So any charged particle that is being accelerated or pulled perpendicular to its motion gives off a type of radiation called synchrotron. Synchrotron radiation is in the radio wave region of the electromagnetic spectrum. So the jets are giving off radio waves. So we've got radio waves prominent up in here. We've got X-rays and all kinds of full spectrum of rays. Of course, it goes from infrared right to the X-rays. That's called a black body spectrum, when it's the complete spectrum of light that's being emitted. So at the center of all spiral galaxies, you're going to have a supermassive black hole. They're all going to have an accretion disk. How much matter is being fed into that accretion disk controls how bright this galactic center is going to be. For example, the Milky Way, Sagittarius A star, is a very quiescent black hole, and very little matter is being fed into the black hole, so we can barely detect any jets. We can still see the accretion disk, and we've taken pictures of the accretion disk, but it's still, very small. And as we progress to higher and higher supermassive black holes that are being fed more and more matter, the more matter that's being fed into the accretion disk, the hotter and more powerful it gets, and the more powerful will be the jets. Such that early in the universe, when we had a lot of matter around and a lot was being fed into supermassive black holes, we get what are called quasars. And quasars are simply supermassive black holes, especially very early in the universe, that are being fed a lot of matter by their home galaxy. And that matter is being converted via the accretion disk and the magnetic sphere, etc., into jets, which are generating incredible amounts of light, which are beaming out into the universe, which we can see with James Webb Telescope deep into space and with ordinary telescopes. These are quasars. Of course, in the present universe, meaning stuff closer to us that we're seeing, there's almost no quasars around anymore because the galaxies are older now and much less material is being fed in. It's possible new quasars could emerge because two merging galaxies could, theoretically, the black holes and merger could start to generate a lot more matter being sucked in. Now, the other important thing about this idea of the clouds being generated in various sizes and configurations. Of course, out of a chaotic Big Bang, you're going to get these clouds popping out, going in all kinds of different directions. And it just so happens that occasionally they're going to merge. And when two spiral galaxies merge, 99% of the time you get what's called an elliptical galaxy, because the spiral galaxies, when they merge, they're coming in at different angles of spin, and so that coherent spin is lost. And no longer do you have that organizing force of coherent spin. So you get a huge, what we call elliptical galaxy, which is twice the size of the original galaxy, but no longer has this coherent spin and beautiful spiral motion. And of course, these collisions or mergers or flybys, if you will, could have happened at any point after the Big Bang, including periods before the light could even be emitted from them at the cosmic microwave background stage. And of course, since then, they could be merging. And if it happens, for example, that two spinning spiral galaxies are merging in just the right orientation so that their spins enhance each other. In other words, they're spinning both the same way, and when they join up, it just so happens that it creates just a bigger galaxy, all still spinning. Then you can have a super giant spiral galaxy. But most times, you're going to just merge in a more random orientation, so you lose the coherence of spin, and you're going to get a huge elliptical galaxy. So when James Webb is showing us these huge early galaxies that don't have much shape, perhaps already, to baby spiral galaxies, if you will, have already emerged. And even at the cosmic microwave background stage, and a few 100 million years after that, when we first witnessed them, already they're very big and more luminous, because perhaps earlier in elliptical galaxy formation, when there's merger, you get a lot of star formation. Now elliptical galaxies tend to be redder because there's not much going on. Of course, in elliptical galaxies, you don't have the coherent spin of dark matter tending to push hydrogen, helium down and actually spur star formation. So, in summary, the new James Webb images showing that this galaxies formed very early is no surprise. Now that we're quite certain of dark matter, again, the evidence for dark matter is very strong, and it comes from numerous pieces of evidence that are completely separate from each other, so it's not one piece of evidence. And it shows that spiral galaxies are the key galaxy. The coherent spin is the attractor in chaos theory, if you will. It's the coherence that brings beautiful pattern from chaos. Out of a chaotic Big Bang, you get beautiful spiral galaxies. Spiral galaxies formation. You can thank cooled dark matter. My name is Romeo Bruni.